Imagine the most powerful, most enigmatic entities in the universe. Things that defy our everyday understanding, not just exploding stars, those are merely the fireworks display. Or colliding galaxies, grand spectacles of cosmic proportions, but something far more profound, something that warps space and time itself. Black holes. These are the true heavyweights of the cosmos. They aren't empty voids, as one might initially think, but matter crushed into an impossibly small space, a singularity where the known laws of physics begin to bend and break. Picture the entire Earth, our home, our planet, squeezed down to the size of a sugar cube. Its gravity would be so intense, so overwhelmingly powerful, that not even light, the fastest thing in the universe, could escape its grasp. This point of no return, this inescapable boundary, is called the event horizon. Cross it, and there's no going back. Most black holes are born from the dramatic collapse of massive stars, stars far, far larger and more luminous than our own sun. When these giants, after burning through their vast reserves of nuclear fuel, gravity wins the ultimate tug of war, and the core collapses in on itself. The result is a spectacular supernova explosion, leaving behind, in some cases, the ultimate remnant, a black hole. But not all stars meet such a dramatic end. Our sun, for example, a relatively modest star, will eventually become a white dwarf, a dense but stable remnant, not a black hole. Only stars at least 20 times more massive than the sun, these truly colossal stars, possess the gravitational might to collapse into black holes. These stellar mass black holes, the remnants of these fallen giants, are scattered throughout galaxies like cosmic crumbs left behind after a feast. They are essentially invisible, lurking in the darkness unless they happen to be feeding on nearby matter, pulling it in with their immense gravity. Black holes are gravity taken to its absolute extreme, a point where our everyday intuition fails us. They warp space-time so dramatically, so profoundly, that our usual understanding of physics simply breaks down, leaving us grappling with the unknown. Near a black hole, time slows down relative to distant observers, and what we perceive as straight lines curve and bend under the immense gravitational influence. They are, in essence, natural laboratories, cosmic test chambers for the laws of physics under conditions we simply cannot replicate here on Earth. By studying these enigmatic objects, we catch a glimpse, however fleeting, of the fundamental structure of reality, the very fabric of the cosmos. Black holes challenge our understanding of the universe's ultimate fate, forcing us to confront the deepest mysteries of existence. They are, without a doubt, the ultimate cosmic enigmas, forever beckoning us to explore the unknown. While stellar mass black holes are impressive cosmic entities, representing the collapsed cores of massive stars, supermassive black holes are the true titans of the cosmos. These behemoths reside at the hearts of galaxies, influencing their structure and evolution in profound ways. Nearly every large galaxy, including our own Milky Way, has one of these gravitational powerhouses at its core, a silent guardian shaping the galactic landscape. But even among these giants, these cosmic leviathans that dwarf stellar mass black holes, one stands above the rest, a record holder in the Black Hole Hall of Fame, Ton 618. Ton 618 is not just large, it is the largest black hole ever discovered, pushing the boundaries of our understanding of these enigmatic objects. It's an ultra-massive black hole, a classification reserved for the most extreme examples of gravitational collapse. Its scale is almost beyond comprehension, dwarfing even other supermassive black holes and redefining what we mean by massive in a cosmic context. Ton 618 is located within a distant ancient galaxy, a relic from the early universe. So far away that the light we observe from it began traveling to us over 10 billion years ago, a testament to the vastness of space and time. When its light started its long journey across the cosmos, carrying information about this distant giant, our own Earth didn't even exist. The solar system was still in its infancy. Observing Ton 618 is akin to peering into a cosmic time machine, allowing us to witness the universe as it was in its formative years. We are essentially seeing the universe in its youth, a period of rapid change and intense activity. Its existence, so early in cosmic history when the universe was still relatively young, presents a significant challenge to our current models of how black holes and their host galaxies form and evolve together. Did it grow to such an enormous size rapidly, consuming vast amounts of matter in a cosmic feeding frenzy? Or did it perhaps form from the direct collapse of a massive primordial gas cloud, bypassing the more conventional routes of black hole formation? TON 618 is more than just a black hole. It's a crucial puzzle piece from the dawn of time, a cosmic enigma. By studying it, we can unlock valuable insights into the early universe and gain a deeper understanding of the fundamental processes that govern the evolution of the cosmos. The story of TON 618's discovery is a fascinating journey that began with a seemingly simple quest: the search for faint blue stars scattered across the vast expanse of the night sky. This search commenced in 1957, a time when astronomical observation relied heavily on meticulous examination of photographic plates. This ambitious project was undertaken at the Tonantzintla Observatory, nestled high in the mountains of Mexico, a location chosen for its clear, dark skies, perfect for peering into the deepest reaches of space. Among the countless celestial objects captured on these photographic plates, one particular point of light stood out. Catalogued as the 618th entry in a specific survey, it appeared as a faint blue point of light, indistinguishable from many other stars at first glance. At the time, its true nature remained a mystery, its significance hidden behind its unassuming appearance, its true nature unknown. For over a decade, astronomers considered it to be just another ordinary star, a background object in the grand cosmic tapestry. It was filed away, awaiting further scrutiny. But in the 1970s, a new technique emerged that would revolutionize our understanding of the universe: spectroscopy. Astronomers use spectroscopy, carefully analyzing the light emitted by celestial objects. And when they turned their spectroscopic gaze towards TON 618, they found something astonishing. It wasn't a star at all, but a quasar, a far more exotic and energetic phenomenon. Quasars are the intensely bright, active centers of distant galaxies, radiating immense amounts of energy across the electromagnetic spectrum. This incredible energy output is powered by supermassive black holes, millions or even billions of times the mass of our Sun, voraciously consuming matter. Further analysis of TON 618's light revealed that it was massively redshifted. Its wavelength stretched towards the red end of the spectrum. This redshift provided crucial information confirming its incredible distance, over 10 billion light-years away, placing it in the early universe. The faint blue dot, once mistaken for a star, was actually a beacon from the early universe, a messenger from a time when the cosmos was much younger and more chaotic. This remarkable discovery transformed TON 618 from a mere catalogue entry, an obscure listing in an astronomical survey, into one of the most powerful and luminous objects ever observed in the known universe, a true cosmic giant. Its quasar status revealed a gravitational engine of unimaginable scale, a supermassive black hole relentlessly feeding on surrounding matter. The hunt was on to understand the powerhouse behind this cosmic lighthouse, to unravel the mysteries of its immense energy output and the black hole at its heart. TON 618 became a key to unlocking the secrets of the distant cosmos, offering invaluable insights into the formation and evolution of galaxies and supermassive black holes in the early universe. What sets TON 618 apart is its staggering mass, about 66 billion times that of our Sun. That's more massive than many entire galaxies. All this mass is packed into a single point, hidden behind a colossal event horizon. Most supermassive black holes are millions of solar masses. TON 618 is in a class of its own. Its event horizon is about 400 billion kilometers across, over 40 times the distance from the Sun to Neptune. If placed at our solar system's center, it would swallow every planet and reach deep into the Oort cloud. Its existence forces astronomers to reconsider how big black holes can get. There must be a limit, as feeding black holes eventually push away in falling material. For TON 618 to reach its size, it must have grown at an extraordinary rate in the early universe. It's a cosmic giant that challenges our understanding of black hole growth. How do you weigh something invisible and billions of light years away? Astronomers study the brilliant light from TON 618's quasar, produced by its accretion disk. They use reverberation mapping, watching for flickers in brightness and measuring how quickly surrounding gas clouds respond. By timing these delays and measuring the speed of the orbiting gas, they calculate the black hole's mass. The gas moves at thousands of kilometers per second, whipped by immense gravity. These measurements, combined with the laws of gravity, reveal ton 618's mass. The result, a black hole with 66 billion solar masses. It's a triumph of astronomical detective work. Ton 618 is visible from over 10 billion light-years away because it's a quasar, one of the brightest objects in the universe. Its luminosity is about 140 trillion times that of our Sun. All this energy comes from its accretion disk, where matter spirals in at near light speed, heating up and glowing fiercely. The black hole itself emits no light. It's the feeding process that creates this cosmic beacon. Quasars like ton 618 were common in the early universe when galaxies were young and full of gas. As galaxies aged and fuel ran out, quasars faded, leaving behind quiet black holes. Ton 618 offers a glimpse into this energetic, violent era. Its powerful radiation and jets can shape the evolution of its host galaxy, regulating star formation. The numbers behind ton 618 are almost impossible to grasp. 66 billion solar masses, more than many small galaxies. Its event horizon spans 400 billion kilometers. Voyager 1 would take over 800 years to cross it. Its luminosity is so immense it releases more energy in a second than our Sun will in its entire lifetime. Ton 618 shines at the Eddington limit, feeding as fast as physics allows. The black hole is still growing, consuming several suns' worth of material each year. Over millions of years, this steady diet keeps it at the top of the cosmic food chain. It's a living, growing monster, a testament to the extreme physics of the early universe. Ton 618 dwarfs anything we see forming today. It's a true heavyweight champion of the cosmos. Ton 618 is full of fascinating details. Near its event horizon, time slows dramatically. An object falling in would appear frozen to a distant observer. Its accretion disk glows across the electromagnetic spectrum, from radio waves to X-rays. The quasar's glare outshines its entire host galaxy, making the stars around it nearly invisible. Astronomers have detected a faint haze of starlight, confirming ton 618's galactic home. If you fell into ton 618, the tidal forces at the event horizon would be surprisingly gentle. You'd cross the point of no return without noticing. The true danger lies in the inevitable journey toward the singularity at its core. Ton 618 is more than a record holder, it's a key to understanding the universe. Its existence so early in cosmic history challenges our models of galaxy and black hole formation. Studying its light reveals not just the black hole, but the structure of the universe between us and it. Ton 618 acts as a cosmic lamp, illuminating the vast web of matter that spans the cosmos. It's also a laboratory for testing Einstein's theory of general relativity under extreme conditions. Every observation that matches relativity strengthens our understanding of gravity. Ton 618 connects us to the grand story of the universe's evolution. It reminds us of the extremes that exist beyond our everyday experience. In seeking to understand ton 618, we confront the deepest questions about our cosmic origins and our place in the universe. Imagine a place far removed from our everyday experiences, a realm where the familiar laws of physics bend and break. Imagine a place in the universe where gravity is so strong that not even light, the fastest thing we know, can escape. A black hole. It's not an empty hole, a void in space, but matter packed into an incredibly small area, a point of almost infinite density. This extreme concentration of mass warps the very fabric of space and time around it. We can't see black holes directly, they remain elusive, hidden from our direct observation. They're invisible, trapping all light and any other form of electromagnetic radiation that ventures too close. So how do we know they exist, if they are impossible to see? By watching their effects, we observe stars orbiting empty space, seemingly held captive by an unseen force. We see jets of energy shooting out from the poles of these invisible objects, powerful beams of radiation, and we witness matter swirling around an unseen force, forming a superheated disk of gas and dust. It's like seeing leaves dance in the wind, a subtle yet powerful indication of something unseen. You can't see the wind itself, but you see its power as it bends the trees and scatters the leaves. Black holes challenge our understanding of physics and reality itself, pushing the limits of what we know. What happens to things that fall in as they cross the event horizon? Where do they go and what becomes of them? These questions push the boundaries of science, driving us to explore the unknown. Among the universe's countless wonders, from swirling galaxies to vibrant nebulae, black holes stand out as the most mysterious, enigmatic, and powerful objects we know. Let's begin a journey to uncover their secrets, a quest to understand these cosmic enigmas. We'll explore where they come from, tracing their origins back to the life cycle of stars. We'll delve into what they're made of, examining the extreme physics at play within these collapsed objects, and we'll consider what they reveal about the cosmos and the fundamental laws that govern our universe. This story starts with the life and death of stars, the cosmic furnaces that forge the elements. By studying black holes using the most advanced telescopes and instruments, we shed light on the deepest questions about existence, unlocking new insights into the nature of reality. Join us as we journey into the heart of darkness, into the unknown depths of black holes, to find a deeper understanding of the light, to illuminate the mysteries of the cosmos. The adventure begins now, as we embark on this incredible journey of discovery. To understand the enigmatic nature of black holes, those cosmic vacuum cleaners that warp space and time, we must first understand the lives and deaths of stars, the celestial beacons that illuminate the universe. These stellar objects are the key to unlocking the secrets of black hole formation. Stars are essentially gigantic nuclear fusion factories, immense spheres of plasma, relentlessly crushing hydrogen atoms together to form helium, a process that releases tremendous amounts of energy. This ongoing nuclear reaction is what fuels a star's brilliance, releasing immense energy in the form of light and heat. This outward flow of energy, a stellar wind composed of charged particles, pushes outward against the star's own gravity, carefully balancing the relentless inward pull of gravity, preventing the star from collapsing in on itself. For billions of years, this delicate equilibrium allows a star to remain remarkably stable, shining steadily and supporting the potential for life on orbiting planets like our own Earth. But a star's supply of hydrogen fuel is ultimately finite, a cosmic constraint. When the hydrogen fuel begins to dwindle and eventually runs out, the outward pressure weakens, and gravity's grip tightens, inevitably taking over. The star's core, now primarily composed of helium, begins to contract under its own weight, causing it to heat up dramatically. This intense heat allows the star to begin fusing heavier elements, such as carbon and oxygen, in a desperate attempt to maintain equilibrium. For stars with masses similar to our Sun, this process eventually leads to a dramatic red giant phase, followed by the relatively peaceful formation of a white dwarf remnant. However, for stars that are at least 10 times more massive than our Sun, behemoths of the cosmos, the story takes a far more dramatic and cataclysmic turn. These stellar giants fuse heavier and heavier elements at an accelerated rate, creating a layered structure, much like the concentric rings of an onion. Each successive stage of nuclear burning happens at an increasingly faster pace, a desperate race against gravity, with the heaviest elements like iron accumulating at the very core of the star. Eventually, this massive star reaches the end of its life cycle, culminating in a spectacular and incredibly violent supernova explosion. The stage is now set for a truly awe-inspiring cosmic finale, a dramatic display of stellar death. Because the ultimate fate of these exceptionally massive stars leads directly to the birth of one of the most mysterious and powerful objects in the universe: black holes. Their explosive deaths are not merely endings, marking the cessation of stellar existence, but rather the genesis, the very beginnings of something far stranger and more profound than we can easily imagine. So let's delve deeper and see what happens next in this cosmic drama. For the most massive stars, the end comes when their cores fill with iron. Fusion can't extract energy from iron, so the star's power source shuts down, Gravity wins and the core collapses in a fraction of a second. The outer layers crash inward, then rebound in a colossal explosion, a supernova. For a brief moment, the star outshines its entire galaxy. The explosion scatters heavy elements, oxygen, carbon, iron, across the cosmos. These elements become the building blocks for new stars, planets, and life itself. We are quite literally made of stardust. But what about the core left behind? For the most massive stars, it becomes something even more extreme, a black hole. The universe's most powerful event gives birth to its most mysterious object. After a supernova, the fate of the core depends on its mass. If it's massive enough, over 3 times the sun's mass, gravity overwhelms all forces. The core collapses, shrinking and growing denser, warping space and time. Imagine a bowling ball on a rubber sheet, but far more extreme. The escape velocity soon exceeds the speed of light. Nothing can escape, not even light itself. At this point, a black hole is born. Its boundary, the event horizon, marks the point of no return. The star's mass is now hidden within this invisible boundary. The star is gone, but its gravity remains more powerful than ever. A black hole is a silent testament to gravity's ultimate victory. The life cycle ends not in dust, but in a rupture in reality itself. This is the birth of a stellar mass black hole. Forged in the death of a cosmic giant, it now lurks in the darkness. The event horizon is arguably the most famous feature of a black hole, capturing the imagination of scientists and science fiction enthusiasts alike. It represents a point of no return, a boundary shrouded in mystery and intrigue. A one-way door into the unknown, a cosmic threshold that once crossed offers no turning back. It's a concept that challenges our understanding of space, time, and the very fabric of reality. It's not a solid surface that you could touch or bounce off of, but rather an invisible boundary, a region in space-time. Imagine an ethereal sphere surrounding the black hole. Anything crossing it, whether it's matter, energy, or even information, is irretrievably lost forever, swallowed by the immense gravitational pull. Even light, the fastest thing in the universe, can't escape the black hole's grip once it crosses this boundary. It's trapped, adding to the black hole's mass and further distorting space-time. The size of the event horizon is directly proportional to the black hole's mass. The more massive the black hole, the larger its event horizon becomes. This size is precisely measured by what we call the Schwarzschild radius, a critical value in understanding black hole physics. To put it into perspective, a black hole with the same mass as our Sun would have a surprisingly small event horizon, just about 3 kilometers wide, smaller than many cities. On the other end of the spectrum, supermassive black holes like Sagittarius A*, residing at the heart of our Milky Way galaxy, boast event horizons that stretch across millions of kilometers, dwarfing the orbits of planets in our solar system. Consequently, anything crossing the event horizon is inevitably doomed to fall inward towards the singularity. Once you're past that point, no rocket, no conceivable force, no matter how powerful, can provide an escape. Inside the event horizon, space-time itself is warped and distorted so severely that it flows inward faster than the speed of light. Therefore, the event horizon represents the ultimate boundary of our knowledge, a limit to what we can directly observe and understand about the universe. However, outside this boundary, we can still make accurate predictions about the behavior of objects, calculate their orbits, and understand how light bends around the black hole. All thanks to the groundbreaking theories of Einstein's relativity. But as we approach and cross the event horizon, our current theories begin to break down, revealing the limitations of our understanding. The event horizon effectively hides a place of unimaginable extremes, where the laws of physics as we know them cease to apply. In essence, it's a cosmic veil, a curtain drawn across a region of space-time, separating our familiar world from a realm of profound mystery, a place where the universe operates under conditions we can barely comprehend. And so, what lies beyond the event horizon, within the heart of a black hole, remains hidden from our direct observation, and continues to fuel scientific debate and speculation. The event horizon is therefore more than just a boundary. It's where science meets the unknown, a constant reminder of the vastness and complexity of the universe. Cross the event horizon, and you're drawn to the black hole's heart, the singularity. Here, all the mass is crushed into an infinitely small, dense point. Space and time break down. Our physics can't describe what happens. The singularity isn't a place, but a moment in the future for anything that falls in. It's the end of the line, an unsolved puzzle for science. Most physicists believe we need a new theory combining relativity and quantum mechanics to truly understand it. Until then, the singularity remains one of science's greatest mysteries. The event horizon hides this secret, locking it away from observation. What really happens at the core of a black hole? For now, it's a cosmic secret. Black holes inspire myths, like the idea they suck up everything in their path. In reality, their gravity is only extreme up close. If our sun became a black hole, Earth's orbit wouldn't change. Another myth: black holes are portals or wormholes to other universes. While wormholes are possible in theory, real black holes would destroy anything that falls in through spaghettification, being stretched by gravity. Time also behaves strangely near a black hole. Gravity slows it down, a phenomenon called gravitational time dilation. Orbiting close to a black hole, your clock would tick slower than on Earth. You'd travel into the future. Most mind-bending of all, black holes aren't entirely black. Stephen Hawking showed they emit tiny amounts of radiation, Hawking radiation. Over unimaginable timescales, black holes can evaporate and disappear. This discovery links gravity, quantum mechanics, and thermodynamics in a profound way. Black holes are stranger and more fascinating than any myth. What would it feel like to fall into a black hole? It depends on the black hole's size. For a small stellar mass black hole, tidal forces would stretch you apart, spaghettification, before you even reach the event horizon. You'd be torn into atoms, never crossing the boundary alive. For a supermassive black hole, the event horizon is gentler. You could cross it intact, not noticing the moment you pass the point of no return. Inside, the universe behind you shrinks to a point of light. Your fate is sealed. As you approach the singularity, tidal forces eventually tear you apart. For a brief time, you exist inside, cut off from the universe. To an outside observer, you'd appear to freeze at the event horizon, fading away as your light redshifts. Falling into a black hole is a journey into the unknown, one way and final. Why study black holes? They're the ultimate laboratories for physics, pushing gravity to its limits. By observing them, we test our theories, like Einstein's relativity, under extreme conditions. Black holes help us understand the life cycles of stars and the evolution of galaxies. Supermassive black holes shape galaxies, influencing star formation across vast distances. They force us to confront the biggest questions in science, like uniting gravity and quantum mechanics. Black holes are signposts pointing toward a deeper understanding of reality. Every discovery, an image of a black hole's shadow or gravitational waves from merging black holes, expands our knowledge. They represent the edge of the known, where curiosity drives us forward. In the universe's darkest corners, we find the brightest insights. Black holes remind us the unknown is where discovery begins. There are places in the universe where the laws of physics are pushed to their absolute limits. Black holes. These aren't empty voids, but colossal amounts of matter squeezed into an impossibly small space. Their gravity is so immense that nothing, not even light, can escape. That's why they're black. The ultimate cosmic prison, swallowing everything that strays too close. Black holes represent a frontier of our understanding, where even Einstein's theories begin to falter. Imagine a star many times more massive than our sun, burning for millions of years until its fuel runs out. In a final, catastrophic moment, the star collapses, triggering a supernova that can outshine an entire galaxy. What's left is a remnant so dense it punches a hole in space-time. A black hole is born. We can't see black holes directly, but we observe their effects. Stars orbiting invisible points, and glowing disks of superheated gas swirling around them. This material emits X-rays as it's torn apart, giving us indirect evidence of these cosmic monsters. These observations are our only windows into black holes, providing clues to the physics at the edge of the abyss. They challenge our perception of reality and force us to confront the profound mysteries of existence. The story of a black hole begins with the life and death of a massive star far larger than our sun. For millions of years, it fuses elements in its core, balancing the outward push of energy with the inward pull of gravity. But when iron forms in the core, fusion stops releasing energy, and gravity wins. The core collapses in a fraction of a second, triggering a supernova, one of the universe's most spectacular events. The explosion scatters heavy elements across space, seeding new stars, planets, and life itself. While the outer layers are blasted away, the fate of the core depends on its mass. If it's massive enough, over 3 times the mass of our Sun, nothing can stop its collapse. It shrinks past the density of an atomic nucleus, becoming a singularity, a point of infinite density and zero volume. The gravity of this point carves out a region of space-time from which nothing can escape. A black hole is born from the ashes of a star. These cosmic remnants are the ultimate endpoints of stellar evolution. Their formation marks the beginning of a new mystery in the universe. The collapse of a massive star's core is a journey into extreme physics. If the core's mass is below a certain limit, it becomes a neutron star, an object so dense a teaspoon would weigh billions of tons. But for the most massive stars, even neutron degeneracy can't stop gravity. The core collapses relentlessly, squeezing into an ever smaller volume. As density skyrockets, gravity warps space-time dramatically, and our known laws of physics break down. This unstoppable collapse creates the event horizon, the black hole's defining feature. The event horizon isn't a physical surface, but a boundary. Once crossed, escape is impossible. Anything crossing it, matter, light, even information, is trapped forever. From a distance, objects falling in appear to slow down and fade away due to gravitational time dilation. But for the object itself, time passes normally and it crosses the event horizon in a finite moment. The event horizon is the ultimate point of no return. Beyond it, the fate of everything is sealed. Imagine watching a probe fall toward a black hole. As it nears the event horizon, its clock appears to slow, its image reddens and fades, seemingly frozen at the edge. This is gravity bending not just space, but time itself. For the probe, though, nothing dramatic happens as it crosses the event horizon. It simply passes through, unaware it's crossed a boundary. Inside, space-time is so warped that the path to the center is no longer a direction in space, but in time, the future. Every possible path leads inevitably to the singularity. Trying to escape would be like trying to travel backward in time. Impossible. The pull of gravity becomes the relentless march of time itself. The size of the event horizon, or Schwarzschild radius, depends on the black hole's mass. For a solar mass black hole, it's about 3 kilometers. For a supermassive black hole, it can be larger than the orbit of planets. The journey across a supermassive black hole's horizon could be gentle, while a smaller black hole's would be violent. No matter the size, crossing the event horizon seals your fate. The singularity awaits. Falling into a black hole is a one-way trip and a brutal one, especially for smaller black holes. Immense tidal forces near the event horizon stretch. Objects apart, gravity at your feet is far stronger than at your head. This stretching effect is called spaghettification. For a small black hole, you'd be torn apart before even crossing the event horizon. For a supermassive black hole, the gradient is gentler. You might cross the horizon intact, only to be stretched later, deeper inside. The matter spirals toward the center, joining the accretion disk, heating up to millions of degrees. This superheated plasma emits intense X-rays, one of the key ways astronomers detect black holes. We witness the final scream of matter as it's consumed, a last burst of light before vanishing forever. Black holes are not just destroyers, they're cosmic engines, revealing themselves through the energy they unleash. Their violence is a window into the most extreme environments in the universe, and their secrets are written in the light of what they consume. Once inside the event horizon, all paths lead to the center, the singularity. Here, all the mass is crushed into a region of zero volume and infinite density. The laws of physics break down completely. The singularity is a place where space and time lose all meaning. Physicists believe this signals our theories are incomplete. To understand the singularity, we need a theory of quantum gravity, uniting general relativity and quantum mechanics. Some theories suggest quantum effects might prevent a true singularity, compressing matter into a tiny exotic state. Others propose the singularity could be a bridge, a wormhole, to another universe, though there's no evidence for this. The singularity remains the ultimate mystery, a challenge to our understanding of reality. It's the heart of the black hole and the frontier of modern physics. Black holes present one of physics' greatest puzzles, the information paradox. Quantum mechanics says information can never be lost, but black holes seem to erase it forever. Stephen Hawking showed black holes emit faint radiation, Hawking radiation, and can eventually evaporate. But if this radiation is random, the information about what fell in is lost, violating quantum theory. This paradox pits general relativity against quantum mechanics. Physicists have debated, does information escape in the radiation, remain in a remnant, or is our understanding flawed? One leading idea is the holographic principle. All the information inside a black hole is encoded on its event horizon. As the black hole evaporates, this information could be imprinted onto the outgoing radiation. This radical idea suggests the universe itself might be fundamentally holographic. Solving the information paradox could revolutionize our understanding of space, time, and reality. The singularity inspires some of the most speculative ideas in cosmology. What if it's not an end, but a beginning? Some theories suggest a black hole singularity could spawn a new universe, a cosmic big bounce. Our universe might have been born from a black hole in a larger parent universe. This is the multiverse concept. Countless universes, each with different physical laws. Lee Smolin's cosmic natural selection proposes universes that make more black holes have more offspring. String theory offers another twist. Instead of a singularity, a black hole could be a fuzzball, a tangle of strings with no interior. In this model, information isn't lost but becomes part of the fuzzball's structure. These ideas are at the edge of science, impossible to test for now, but serious attempts to unify our theories. By pushing our understanding to the limit, black holes force us to imagine new possibilities for reality. They stretch the boundaries of science and human imagination. Black holes are more than cosmic curiosities. They're fundamental to our understanding of the universe. They test the laws of physics in ways we can't replicate on Earth. Observing black holes lets us probe Einstein's relativity and the behavior of matter in extreme gravity. Supermassive black holes shape galaxies, regulating star formation and galactic evolution. Understanding them is key to understanding the cosmos itself. The quest to unravel their mysteries drives us toward a unified theory of nature. Black holes are where our best theories collide and where new physics may emerge. They force us to confront the deepest questions. What is space? What is time? What is reality? By studying black holes, we illuminate not just the universe's secrets, but the power of human curiosity. In the darkness of black holes, we find the brightest sparks of discovery. The universe is a vast and wondrous place, filled with more stars than grains of sand on Earth. Among all this light, there are places of profound darkness, regions where the laws of physics are pushed to their limits. These are the universe's greatest mystery, black holes. The idea of black holes began not with telescopes, but with Einstein's revolutionary ideas about gravity and space-time. He imagined a universe where massive objects could create a pull so immense that nothing, not even light, could escape. Today we're in a golden age of astronomy, observing these once theoretical objects directly. We've seen their shadows and heard the gravitational echoes they create when they collide. Each discovery brings new questions. What happens inside a black hole? Where does the matter go? In this journey, we'll explore these incredible phenomena, from the collapse of dying stars to the event horizon, the point of no return. Black holes are not just cosmic curiosities, they are fundamental to the universe's story and to our own. They remind us there is still so much left to discover. What exactly is a black hole? It's a question that has captivated scientists and stargazers alike for decades. These enigmatic entities lurk in the depths of space, challenging our understanding of the universe. Simply put, it's a place in space where gravity is so strong that nothing can escape, not even light. Imagine a cosmic vacuum cleaner, relentlessly sucking in everything that ventures too close. Imagine throwing a ball on Earth. If you throw it fast enough, it escapes Earth's gravity. That speed is called escape velocity. Now picture an object far more massive than Earth, a star perhaps many times larger than our own sun, squeezed into a tiny space. Its gravity would be immense. The very fabric of space and time would be warped around it. If you keep making it denser, the escape velocity increases, eventually surpassing the speed of light. At that point, nothing can escape, not a rocket, not even light. This is a black hole, not a hole, but matter crushed into an infinitesimal point. It's a singularity, a place where our understanding of physics breaks down. It's the ultimate victory of gravity. Black holes are black because they don't reflect or emit light. Any light that gets too close is pulled in forever. When we look at a black hole, we see a perfect patch of darkness against the stars. We can only infer their presence by observing their effects on surrounding matter and light. It's a region sealed off from the universe, a one-way door. Here, our everyday intuition about how the world works simply ceases to apply. The laws of physics as we know them are stretched to their breaking point. Black holes challenge everything we know about space, time, and reality. They are the most extreme objects in the cosmos. They hold secrets that could unlock new understandings of the universe. To truly understand the enigmatic nature of black holes, those cosmic vacuum cleaners lurking in the depths of space, we need to fundamentally rethink our understanding of gravity, moving beyond the simple idea of attraction. Einstein's revolutionary theory of general relativity elegantly showed that space and time are not separate entities, but are inextricably woven together, forming a unified four-dimensional fabric we call space-time. This is the stage upon which the cosmic drama unfolds. Mass, any object with mass, bends and warps this fabric of space-time, creating the effect that we perceive and experience as gravity. It's not a force, but a curvature. To visualize this, imagine space-time as a vast, stretched rubber sheet extending in all directions. A marble placed on the sheet makes a small dip, a gentle curve, while a bowling ball, much heavier, creates a deep and significant curve. Planets, in their eternal dance around stars, follow the straightest possible path. But that path appears curved to us because it's moving through this curved space-time, not because they are being actively pulled by any invisible strings or mysterious forces. Now a black hole is like a bowling ball that is unimaginably heavy, so heavy that it doesn't just curve the sheet, it punches a hole straight through the fabric of space-time, creating a bottomless well from which nothing, not even light, can escape. The curvature around a black hole is so incredibly steep and intense that once you venture too close to its boundary, known as the event horizon, you're inevitably pulled in, trapped forever, with absolutely no possibility of escape. And this warping of space-time isn't just a theoretical concept. We can directly observe starlight bending and curving around massive objects in the cosmos, precisely as Einstein's groundbreaking theory predicted many years ago. In the vicinity of black holes, this gravitational bending effect is dramatically magnified, leading to the distortion and magnification of light emanating from distant stars located behind them. This remarkable phenomenon, which we call gravitational lensing, provides us with a powerful tool to detect and study these otherwise invisible cosmic giants. It serves as direct, visible, and compelling proof that black holes possess the extraordinary ability to truly bend and warp the very fabric of the universe around them. In essence, black holes represent the ultimate and most extreme test of Einstein's revolutionary ideas about gravity and space-time. They offer us a profound glimpse into the nature of reality, revealing that gravity is not merely a force, but the very warping of reality itself. Where do black holes come from? Most are born from the death of massive stars. A star's life is a battle between gravity pulling in and nuclear fusion pushing out. For millions of years, this balance holds as the star fuses lighter elements into heavier ones. Eventually, the star runs out of fuel and forms an iron core, a dead end for fusion. With no outward pressure, gravity wins. The core collapses in a fraction of a second. This triggers a supernova explosion, blasting the star's outer layers into space. The explosion scatters heavy elements that will one day form new stars, planets, and life. If the core is massive enough, it collapses beyond all known limits, forming a singularity, a point of infinite density. A black hole is born from the ashes of the dead star. Its gravity is now concentrated into a tiny point, warping space-time and creating an event horizon. The death of a star gives birth to one of the universe's most mysterious objects. Black holes are the ultimate end and a new beginning. They are the cosmic legacy of dying giants. Every black hole, a cosmic enigma, is surrounded by a boundary, a spherical surface that marks a point of no return. This boundary is known as the event horizon, a point of no return from which nothing, not even light, can escape the black hole's relentless gravitational pull. It's not a physical surface you could touch or bump into, but rather a theoretical threshold, a critical point in the fabric of space-time itself. At the event horizon, the force of gravity is so incredibly strong, so overwhelmingly powerful, that the escape velocity required to overcome it equals the speed of light, the fastest speed possible in the universe. Anything that crosses this boundary, whether it's a stray asteroid, a beam of light, or even a curious astronaut, spaceship, planet, or light itself, can never ever escape the black hole's grasp. It's a one-way trip. Imagine for a moment that you're orbiting a black hole in a highly advanced spaceship. From a safe distance, far enough away from the event horizon, you can still fire your engines and escape its pull. But as you approach the event horizon, venturing closer and closer to this invisible boundary, strange and mind-bending things begin to happen. Time itself begins to behave in a way that defies our everyday experience. To you, inside the spaceship, time continues to feel perfectly normal, ticking away at its usual pace. But to a distant observer, watching you from afar with a powerful telescope, your journey appears to slow down dramatically. As you near the event horizon, getting ever closer to that point of no return, you appear to freeze in time, your image becoming fainter and fainter until you eventually seem to fade away completely. From your perspective, however, you cross the event horizon without noticing anything particularly special or dramatic. But once you're inside, once you've crossed that invisible line, your fate is irrevocably sealed. All paths, all directions now lead inexorably to the singularity, that infinitely dense point at the very center of the black hole. It's like being swept into a powerful river, a raging torrent that you simply cannot swim against, no matter how hard you try. The current is too strong, the pull is too great, and it always inevitably pulls you in. Inside the event horizon, beyond that point of no return, space-time itself, the very fabric of reality, flows relentlessly toward the singularity. And it does so faster than the speed of light. There's absolutely no turning back, no escape, no way to reverse your course. The event horizon stands as the ultimate boundary in the universe, a cosmic frontier beyond which our understanding of physics begins to falter. Beyond it, within the black hole's embrace, the familiar rules of reality as we know them simply break down, leading to a realm of profound mystery. What would happen if you fell into a black hole? It depends on the black hole's size. For a small, stellar mass black hole, tidal forces would stretch you out, spaghettification, long before you reach the event horizon. The gravity difference between your feet and head would tear you apart atom by atom. For a supermassive black hole, the event horizon is much farther from the center, so the tidal forces are gentler. You could cross the event horizon intact, without being stretched. Inside, you'd see the universe compressed into a bright point above you, surrounded by darkness. You'd be in free fall, unable to escape as space-time carries you toward the center. The journey from event horizon to singularity would be swift and final. Eventually, tidal forces would become infinite, crushing you and your ship into the singularity. No matter the size, the end is always the same: total destruction. Black holes are the universe's ultimate one-way trip. Black holes aren't just cosmic destroyers, they're essential to the universe's structure. Nearly every large galaxy, including our Milky Way, has a supermassive black hole at its center. The bigger the galaxy, the bigger its central black hole, suggesting they grow together. As gas and dust fall in, they form a superheated accretion disk, sometimes shining brighter than the entire galaxy. Not all material falls in, some is blasted out as jets, shaping the galaxy and regulating star formation. These jets act as a feedback system, controlling the growth of galaxies. Black holes recycle matter and energy on a grand scale. Far from being just destroyers, they are cosmic architects. Black holes are key to the evolution of galaxies and the universe itself. If black holes are invisible, how do we find them? We look for their effects: stars orbiting an empty point, or gas heated to millions of degrees as it falls in. At the Milky Way's center, stars whip around an unseen mass, a supermassive black hole. We also detect intense X-rays from accretion disks, evidence of matter being devoured. The most revolutionary method is listening for gravitational waves, ripples in space-time from black hole collisions. In 2015, LIGO and Virgo detected these waves for the first time, opening a new window on the universe. We can now hear black holes merging billions of light years away. Black holes reveal themselves through their powerful influence on their surroundings. Even though we can't see them, we can track their cosmic footprints. Black holes are invisible, but their presence is undeniable. Black holes are the universe's most extreme objects, places where matter is crushed and space-time is warped beyond recognition. They are both destroyers and creators, shaping galaxies and seeding the cosmos with new possibilities. We've explored their origins, their deadly event horizons, and the strange fate of anything that falls in. We find them not by sight, but by their profound effects and the echoes of their collisions. Yet the greatest mysteries remain. What happens at the singularity? Is information lost forever? Black holes push us to the frontier of knowledge, challenging our understanding of reality. They remind us that the universe is stranger and more wonderful than we can imagine. The story of black holes is far from over, and so is our journey to understand them.